Hello everybody. In this notebook, we are going to learn how to train an image classifier using transfer learning. Now, if you don't understand what that means, let me explain. First of all, in this notebook, we are going to use Caltech 256 dataset. Now, as the name suggests, it was created by a team in Caltech. It has 256 different classes, but for this notebook, we are going to use a subset of that data set. We are going to use only 10 classes instead of 256 classes, just so it trains faster. We are also going to use a neural network called ResNet 50. This is a very popular neural network architecture, and it has 50 different classes. So we are going to use this in our transfer learning. So, I'm not going to show you this image. You can blow it up and see it yourself. Before we go into what does transfer learning mean, let's look at a typical neural network architecture. We usually have an input layer, which is basically takes in an input image of a fixed size, right? So it could be an image of size 256 by 256, or more commonly it is 224 by 224. So basically you take a 256 by 256 image and take the middle portion of it, right? Which is 224 by 224. And typically, you may be thinking that, oh, why do we do that? To account for padding on the two sides. So we account for some padding. And then we have something called a feature extractor. So we have a collection of convolutional layers which serve as feature extractors. So what are features? Features are representations of image which make it easy to classify, right? So pixels, you can also think of pixels as features, but pixels are not very good features, right? The features that we are looking for are useful in differentiating between two classes. In the image classification problem, we want to find features which are useful in separating different classes. So the features would be similar for images of the same class. For example, if you look at images of all the dogs, then the features would be similar. And the features for, let's say, all the cats, they would be different. So they would form clusters. That is the goal of, a feature extractor. So from the image, we have this bank of convolutional layers, which gives us the features. And finally, once you have these features, we want to create a classifier, right? A classifier basically takes these features and then is able to tell them apart. One simple classifier you can think about it is, let's say we had only two classes, cats and dogs. And they formed, after the feature extraction step, in a higher dimensional space, they will form two different clusters. Now to find which cluster it is in, we can have a classifier that creates a plane between them, right? If you're on this side of the plane, you're in the dog class. If you're on this side of the plane, you are in the cat class. So that is what a classifier does. So these, in a neural network, typically the classifier part consists of fully connected layers, just the kind of layers we had seen in a multi-layer perceptron. They are fully connected. These layers are different. These are for images. These are convolutional layers, which are different. So we have a feature extractor and we have a classifier, and the classifier takes all these features and converts it to class labels, which is the output we want. So one way to use, let's say you have a pre-trained neural network like ResNet 50. The way it works is we have this feature extractor, we have the classifier. If you use ResNet 50 directly, with the pre-trained model, it was trained on 1,000 different classes, right? So it's going to output, if what you're looking for is among those 1,000 classes, then great, you can pretty much use ResNet 50 directly, okay? And get the output. So the great thing about this is that it requires no training, right? And it is good for classifying images if your image is one of these 1,000 classes, right? Cats, dogs, and you can look at all the 1,000 classes. The second thing you could do is, okay, you have this architecture, right? So a neural network, a pre-trained neural network has two parts. One is the architecture, which says that, oh, what are the different kinds of layers inside the neural network. And then we have weights and biases. Those are basically, after training, you get the right weights and biases. As I said, that a neural network, if you think about it as a black box, there are these knob settings. When the knob settings are right, then you get the right answer. And so these weights and biases are those knobs. And so one way to train a neural network is use only the architecture, right? The weights that you had trained on, you can throw them away, right? Because you want to have a new data set. Now, this is not a very good idea. It's usually, it's a very good idea to use a pre-trained weight and start from there, and then, modify the neural network for your purpose. But it is entirely possible to completely throw away these weights, start with random weights and train your neural network. And this can take, weeks to train the neural network, but it is possible. So this second line, almost never are you going to use this, okay? So the third option is to fine tune, to do transfer learning. In transfer learning, we freeze these, the pre-trained, the classifier part of it, the feature extractor part of it. We completely freeze it, we don't update those, and we train only the classifier part of the neural network, okay? So this is great because you are standing on the shoulders of giants. Somebody has already trained the feature extractor for you, and you're using it. And even though the feature extractor was not trained on your data, it can be very useful for a different data set, okay? And because the classifier, you have feature extractor, which was used for, for classifying these 1,000 classes, there's a very good chance that it will be sufficiently good if you want to use it on your data set. Okay, so this is one option. The other option is that, and this is very useful when you do not have a lot of data. When you do not have a lot of data, use transfer learning. Now, let's say you do have a lot of data, right? And you just don't want to train just the final few classifiers, just the classifier part. You want to fine tune part of the pre-trained network also. And that's perfectly fine. You can do that. The computation will be slightly heavy. You will need to get more data for it, right? So that's the difference between transfer learning and fine tuning. Both of them are used extensively based on the amount of data you have, based on the amount of computational power you're ready to spend. The easiest one of them is called transfer learning. And in this notebook, we will focus on transfer learning. In the next notebook, we'll tell you how to do fine tuning. All right, so let's get started. So we start with this code. As always, we are going to install Torch info. We are going to import a bunch of libraries that are important for, you have seen most of these libraries. Some of these libraries are new, like the zip file, the requests for downloading, and so on and so forth. But you can look at the comments to know what are the different ones we are importing and for what reason. All right. So this is a simple utility function for downloading a file, and then we are going to download this zip file, which basically contains a subset of Caltech 256. And the number of images that we have in this, let's just do this extraction with, using this code basically helps us extract the zip file. And these are the 10 categories we have inside that zip file. Basically a few different animals. And there are training samples, 60 training samples per category. And there are 10 validation examples and 10 test samples. Now, when you train a neural network, usually you divide the data into 3 parts: training set, validation set, and test set. Training set is the data on which the neural network is trained. Validation set is the data on which you test the accuracy. But if you have multiple training runs and you're using this validation set again and again to test the accuracy, if the accuracy is not good, you're going to change some parameters. So even though you're not using the validation set directly, you are indirectly fixing the training process if you don't get good accuracy on the validation set. So there is some, some information that is being sent in your training process, even though there is explicitly you're not actually using the validation set to train the model, but there is this implicit training happening. That is why we have a separate set, completely separate set, which is called a test set, on which you report the final numbers, right? And that is done only once, right? At the end of everything, you say that, okay, your model is ready. Then you test it on this test set. Sometimes this is also held out. You don't have access to this test set. You submit your model to a different person, and then they run it on this test set and give you the final accuracy. That is why the test set is used. Now, we are going to use different image transforms during the training, validation, and test. First of all, when we read the image, we are going to randomly resize the image and crop it, right? And you can see that the size of the image finally is going to be 256 by 256, and there is some random scaling also, right? So you can scale between 0.8 to 1, so which means that we can resize the image, make it smaller, and 1. So this kind of thing is called data augmentation, where you take the original image or original training set, manipulate it before training, right? So that you get more variety. Here we are also doing random rotations, and we are going to say that, okay, plus minus 15-degree rotation is allowed. And we are also going to horizontally flip the images. This is again, these are augmentation strategies, because we got some image, and we are creating augmented versions, modified versions of the original image. What this does is it creates more variety in the image, right? So these kinds of augmentation strategies are very good when you have limited data. You can create a whole lot of more data using these augmentation strategies. And then finally, once we have done all these augmentations, we are going to center crop, because this network takes a 224 by 224 image. Okay, we are going to center crop and then convert it to a tensor, and then normalize this based on the mean and the standard deviation. All right, so we have done with that. Now for validation set, we are going to use slightly different transform. We don't need to do any kind of transformation on the validation set, because this is where we test the accuracy. So we simply use resizing and center cropping, convert it to a tensor, then normalize the image. For test set also, it is exactly the same. We are going to resize the image, center crop it, convert it to a tensor, and then normalize the image. Okay. Now, once we have done that, we are going to specify what is the training directory. And this is just based on how we have structured the data set that we zipped up and sent to you. So basically, there are three directories: train, valid for validation, and test. We are going to use a batch size of 32. The number of classes is basically 10. And you can print the number of classes. You can see here there are 10 classes. We know that. And then we create this dictionary of train, validation, and test. And basically this contains the data sets, right? We are creating data sets from these three kinds of images. We have the training set, we are applying the transforms to the training set and creating a data set. And similarly, we are creating the validation and the test set. And then we are getting a mapping from the image class to the class name, right? We are giving it an ID, which you can see here. 0 is basically bear, 1 is chimp, etc. Right? So this is being done in this piece of code, and then we are printing it. Finally, we are looking at the length of the training set, which is 600. We are looking at the length of the validation, 10 per class. So it is 100, and test is 100 also. So this is what you can see here. Now we are going to load the ResNet 50 model with default weights, and then we are going to move it to the device, right? The device, if you have a CPU, it's going to run. If you have a GPU, it is going to run on the GPU. If you have a GPU, you're going to run it on the GPU. Otherwise, it is going to be the CPU. All right. Now, once we have loaded the model, we are going to freeze all the parameters, right? You can see any model that you load, usually the parameters are unfrozen. They can change the weights and biases. So we are going to freeze the entire model because we don't want to retrain the entire model. In transfer learning, we are going to retrain only the last few layers, right, of the classifier. So we are going to set it to false. Next, we basically look at the final fully connected layer in ResNet, and we say, what are the number of features? What is the size of this layer? That we get in FC underscore inputs, right? So, and the comments are also very, detailed. You can see it get the number of input features for the final layer, okay? To that, we are going to add, you can see here, resnet.fc. This is fully connected layer. We are going to add some more layers. So we are going to add, the first layer is a linear layer, which connects the final layer of ResNet 50 to another 256 neurons. So we created a new layer with 256 neurons. We added a ReLU to it. We added dropout to it. We have explained these terms before, so we are not going over it again. And finally, we are ending it with another layer of the output classes. So this is 256 and the number of classes is 10. So you will get an output of 10. And finally, we have this operation, which is the log softmax. So we get, here we get a vector of 10 elements because we have 10 classes, and then we do a softmax on it, right? But we don't do actually softmax. Softmax will turn these into probabilities, right? So all the 10 numbers that you get, it is going to take that vector so that it adds up, all the elements would add up to 1 once we do softmax on it. But this actually, we are doing log of softmax operation on it. And that is because log of softmax is more stable during training. And once we use log of softmax, we use it in the negative log likelihood loss. For multi-class classification, this is usually done. Sometimes you may also see that this is not used. The network ends right here. In that case, people use cross entropy loss. So here, for example, you can see, actually this is, again, I'm correcting this thing in real time. All right. So let's say if sometimes you would see that this log softmax is not there. So here we are getting raw values of the output. And then we have to use a loss function called cross entropy loss. So when we use cross entropy loss, it is the same as first using, it does log softmax and then applies a negative log likelihood loss. So cross entropy loss is basically a combination of these two things. We will see it in the next notebook. Both of these are valid ways of solving it. All right. So once we have done this, we are going to send it to the device, to the CPU or the GPU. And I've already explained the loss function we have to define. This loss function, make sure that, this and this go together, right? For a multi-class classification problem, when we are solving, then this is the right loss function. We also have to provide a learning rate. Learning rate basically specifies how fast the neural network is learning. Now, if it is too fast, then it may lose the local minima. Think about the bowl as the loss function, and if your learning rate is too fast, it is going to miss the minimum. So the loss function has to be such that it is going to gradually settle down. Okay, but if you're seeing that your neural network is not learning fast, then you can try increasing the loss function. We are going to use an optimizer called stochastic gradient descent. Unfortunately, this is a short course and I don't have the time to go over the optimizers, but we cover these optimizers in our paid course, Deep Learning with Pytorch. So this optimizer is, we have to specify the parameters. We are optimizing over all parameters. We are going to mention the learning rate and something called the momentum. So don't worry about these exact parameters. Just imagine that once we get the loss and we get the gradients of the loss function, the optimizer's job is to go and update the weights. So there are some popular optimizers like stochastic gradient descent, which we are using here. In the next notebook, we are going to use the Atom optimizer, which is even more popular. Okay, so we send this information in, and now we are ready to write the training code. All right, so now we are ready to write the training and validation code. In this function, we pass in the model, the loss function, the optimizer, and the number of epochs. So, we start with the time. We want to make sure, we want to calculate how much time it spends for every epoch, etc. We also find the best loss and keep track of all the best epoch as well as the best loss. And we have this history variable so that we can keep track of all the losses, and we'll use this history for plotting. So for each epoch in epochs, which means that we are going to loop over the number of epochs, and then we basically keep track of the time as well. We set the model in training mode. We set the loss to be 0, the accuracy to be 0, the validation loss also set to 0, and the validation accuracy is set to 0. Now we ask the data loader, training data loader, to give us one batch. So remember that in this code we have used a batch of 32. Now so we are going to basically loop over that. We'll get the inputs and the labels. So 32 at a time, and in the final batch there could be smaller than 32 numbers depending on how many the total number of training sets are. All right, so then we set the input to the device. So this is the input image, and we set the label to the device as well. Also keep in mind that the data loader also augments the data. It modifies the data in certain ways that we had mentioned earlier, so that the training data is actually slightly harder than the test and validation data, because the training data is being modified, augmented, rotated sometimes flipped, etc. So then we set the optimizer to 0 grad, which means that we are clearing out the gradients, and then we are going through a forward pass. So the input batch we are going, the entire batch is going through a forward pass. So we get the outputs after the forward pass, which means that it is simply going through the network and we are getting some output. Then we use the loss criterion to find the actual loss. We pass in the outputs that we received as well as the labels that the ground truth labels we had. So we have the output and we have what is the predicted. We have the predicted labels and the actual labels, and that is used to calculate the loss. And this loss that we calculate is a single number, right? And this loss typically would be the average loss over the batch. Now we do a backward propagation on it, and as you know, when we do a backward propagation, we are basically calculating the gradients and propagating the gradients back. Once we do that, we are ready to use the optimizer. Remember, the optimizer is the one that uses these gradients and updates the weight. So here we are basically updating the weights. Next, we keep track of what is the training loss. We take the training loss. This loss.item, this is, as I mentioned, that this is the mean or the average loss over the batch. So that is why we are multiplying it with the batch size. You may be thinking, why can't we just average over, why can't we just keep adding the average loss? The reason is that it may not be the same. The batch size, the last batch size could be much smaller, right? It could be, depending on, it may not be 32 images, it could be even one image, right? So we want to make sure that the training loss is the average loss of that batch times the number of the batch size. And that's the training loss. We'll keep track of it. And then we find in this set, right, how many predictions were correctly made. So we basically take the max prediction for every image, and that is our prediction, okay? To calculate the correct predictions, we basically see when the label is the same as the prediction, right? So whatever label we have assigned, we know from the ground truth, if it is the same as the predicted label, then we are good, and that is what correct counts has. So then we have the accuracy. The accuracy is basically the number of correct counts divided by the total number of images. So we are just calculating the mean. And then we are getting the training accuracy. We are accumulating the average accuracy, right? And then multiplying it by the number of, by the batch size. All right, so this is how, we are calculating in the training step for all the batches, right? For all the batches, we are doing this. And this, as you know, we are going through one epoch. So in one epoch, the entire data set, we are going over the entire data set. The entire data set is divided into smaller batches, and this is what the for loop for the batches is. So at this point, by this step, we have gone over, we have trained the model using one epoch, right? It has gone over all the images at least once. Next, we are going to run the validation error, right? So to do that, we first tell Torch not to calculate the gradients. We set the model in eval mode, and then we loop over the validation set. Again, this validation data loader is going to give us 32 images at a time. We look at the inputs. We actually put these inputs to the GPU or the CPU, as the case may be, send the labels to the device as well, and then we calculate the output. So we do a forward pass on this, and similar to how we calculated the training loss, we are going to calculate the validation loss. We are going to calculate the validation accuracy. This is exactly the same code as the training function. Next, we check whether the validation loss is better than the best loss we have got, right? And if that is the case, then remember, loss should be lower, right? So we update that the best loss is now this loss, and the best epoch is the current epoch, and we save the model for the current epoch because this is the best. Then we calculate the average training loss, we calculate the average training accuracy. Similarly, we calculate the average validation loss, and we calculate the average validation accuracy and put it inside this variable, append it to history, because we are going to use this information for plotting. And then we calculate how much time did this epoch take, and we are printing all that information. All right. Once that is done, we return the model, we return the history and the best epoch. Now, we can also, the ResNet 50 model that we just downloaded, we can look at what is the architecture of this model by sending a dummy variable through it and calling summary. Okay. So this is just a dummy variable. You can see what it does. The structure, the first, shape is 32 by 10. Right, because we are sending 32 images at a time. That is the batch size, and that's that's the input. And then we go over several layers, like this is the convolutional layer, and so on and so forth. There are a bunch of layers, right? We are not going over the exact architecture in this course, but you can see that in the end we have the log softmax. This is the part we added, right? This is the part we added, which is basically, you can see that we added a 256. We added a layer which is 256 in length, and then we also added the output to be 10, right? These are the number of outputs. Okay, so we are ready now. We are going to call the train and validate function that we created earlier. The number of epochs is set to 25, and we basically get the best model, best train model. Once we get the best train model, we also get the history. You can see all this. We can plot it, right? Because in the history variable, we have all the information, and you can see here we are plotting the training loss and the validation loss. Typically, forget about this initial part. In the initial part, things are not very settled, right, so to speak. And there are several reasons why this can actually flip the training loss, and the validation loss can flip. But usually they end up in this situation where the training loss, which is in red color, is lower than the validation loss, which is obvious because the model is looking at this training data and updating itself. So it's trying to minimize the training loss. The validation loss, it doesn't know. It's not using the validation images to update itself. So usually the validation loss, the inaccuracies would be larger. So this is the kind of graph you see. Sometimes if you see that the training loss is low, but the validation error is very high, in that case, you know that the model is trying to overfit. It is memorizing the answers in the training set, and it's not really learning. And there are several ways to fix that problem. One of them is to increase the dropout value. But there are several ways, systematic ways to lower overfitting. But here it worked perfectly. And you can see the accuracy also. The training accuracy is usually higher than the validation accuracy. And what we are looking for is that the gap between these two should not be very large, right? If the gap is very large, then the model is overfitting. Okay. Next, we compute the test accuracy, and the code would be very similar to what we have seen. For test set, it's the same as the validation set, right? All the code, we basically first set the gradient tracking to zero to no, and then we set the model in evaluation mode, which makes the model go faster. And then similarly, we put this inputs to the device, the labels to the device. We get the outputs, we get the loss. From the loss, we basically add up all the losses to get the test loss. And then similarly, we get the test accuracy by adding up all the accuracies. And then we finally tell the average test loss as well as the average test accuracy, and we print it out. So here we basically are loading the model, and then we are basically sending it to compute test set accuracy, right? And this, you can see that after calculating the accuracy on the test set, it is reporting an accuracy of 97%, which is great. So we can see that validation error, the training error would be the lowest. We can go and look at this last. For example, here you can see that the training loss, the training accuracy is 98.6%. And the validation is 95%. There were other models which were slightly better than 95%. Let's see. Yeah, we are getting 94, 95%. Here, 96%. This is probably the one that was stored. And you can see that on the training set also we are doing very well. So this on the test set also we are doing very well. So you can see that the accuracy was 97%. Okay, now we are ready to do inference. Inference basically means using the model to on a new image. And again, this thing is going to look very similar. Okay, so the very first thing is that the image transforms, we have to define image transforms. Whenever we get an image, it needs to be modified in exactly the same way we are modifying any test image, right? So we are applying those image transforms, right? We open an image, we display an image in these lines, and then we convert this image into a tensor by applying all the transforms which are similar to the test image. And then we also need, there is one more thing we need to do. We have to convert this this tensor that we get into this format, because when we read an image, it may not be in the right format. In Pytorch, we have to convert this tensor into this format where the first one is batch size, the second dimension is the number of channels, the third dimension is the height, and finally we have the width, right? Once we have converted this image into a tensor, we need to add this one extra dimension to it so that it can be ready for batch processing. So now, because this is an image and we want to convert it to a batch, so and the batch size is 1, but we still need to convert it into this format. So now we have a tensor which has 4 dimensions and it is ready to be used. We want to make sure that, if CUDA is available, then we convert this into a CUDA, depending on whether it is CPU, GPU, etc. Right now it is on the CPU, and if the GPU, NVIDIA GPU is available, we send it to the NVIDIA GPU. Now, to run the model, again, we are going to say that do not calculate any gradients, do not keep track of gradients. Then we are putting the model in evaluation mode, and when we put the model in evaluation mode, certain things happen differently. For example, the dropout is different, as well as the behavior of the dropout layer, as well as the batch normalization layers. These are slightly different. And then we basically do a forward pass on the image. We get the output. The output, remember when we built the network, the output layer, the final output was log of softmax, right? It was not softmax, it was log of softmax. And to undo the log, we have to do this exponential, right? So the log probabilities that we had need to be undone and using this exponent. And once we do that, we get the probabilities, right? PS stands for probabilities. So once we get these probabilities, we can look at the top 3 and we get what is the score, as well as what is the class, right? And this class is basically a number, and we have to convert it into an ID. So here, from ID to class, this is converting it to a string so that we can display that string, and score is essentially the probability. Okay, so then we print the top 3 predictions. Okay, now we are downloading all these a few images, and you can see that for this image, it says that there is a 99.62% probability that this is a skunk, which is true. Zebra also gives a very high score. Now we also wanted to try a difficult image. You can see that for this model, this doesn't predict llama. This is a llama image, but if you look at, they're wearing glasses, and there is another person here who's wearing a mask. So it gets confused that whether it's a llama or a bear, and this particular model is giving a wrong answer. You can actually train models differently, and you could get a model where the prediction is correct, but we just wanted to include a difficult image. But if you have an easy image, you can see it just nails it, right? So this image is particularly difficult because the image also has the person in it, right? This is basically person and llama, and maybe it thinks that the chimp, it's getting a high score because there's a person there, and sometimes humans and chimps can get confused. So it's a difficult image, the point that I'm trying to make. All right, so that is it. In the next notebook, we are going to cover how to fine-tune this. And remember, in fine-tuning, in transfer learning, we just train the last classifier layer. In case of fine-tuning, we are going to train the some of the layers in the feature layer also, right? And that is the difference between the two. So see you in the next notebook. That is all we wanted to cover in this notebook. Thank you.